Okay, welcome to example number 11. We have a two-block system, equal masses, M1 and M2 are the same mass, so we'll just call them M. And there is coefficients of static and dynamic frictions that are equal to 0.3 for both blocks. So the system is given an initial speed of 0.9 meters per second towards the left-hand side of this system, and we want to know how far it will go. So we want to know what delta x is. Okay, so this is quite a challenging problem. You have to first realize that, well, if it comes to a rest, the final speed is 0. And in order to find the displacement, we need to find out the acceleration of the blocks. And in order to find the acceleration of the blocks, we have to solve this like a free body diagram problem. So we have to look at the entire system and find the acceleration of the entire system, or the individual blocks. So let's first start by drawing a free body diagram and picking appropriate coordinate axes. Okay, so here I've labeled two appropriate coordinate systems, both separate, different ones because they're different inclines here. So now let's start to label the forces. We have the force of gravity on M1 and also the same force of gravity over here on M2. We have the normal force on M2 and we have the normal force on M1. We have a tension on M1 and an equal and opposite tension over here on M2. And then we have the friction. Now remember that the system is moving up here and then down here, so it's moving towards the left. And so that means the friction would oppose the direction that it's sliding. And so we'll have another frictional force here, and we have a frictional force going here. So there are two arrows here. So let's appropriately label everything here. We have M1G here, we have M2G here, we have Fn, we'll call that Fn2, and we have Fn1. We have a force of tension, and we have the force of friction 1. We have the force of tension over here, and we have the force of friction on number 2. And the system is accelerating in the opposite direction that it's moving because it's going to come to a final resting spot. So that means the acceleration is to the right in these directions that I've just shown. Now you could solve this problem in an entire system and have an axes like this and draw them out, or we can treat them individually. Because there's a lot of forces drawn here, I think it'll be easier for us to see them individually. So let's start off with block M1, and I'm going to redraw that cluttered free diagram over here, and I'm going to tilt the axis so maybe it's a little easier for you to see. So here's this block. What I've done is I've taken this block and tilted it. So this is the normal force, Fn1, which is this arrow, but now the whole system's been rotated just slightly. And then we have the tension here. We have the force of friction acting on that body, Ff1. And then we have this force of gravity, Fg1. Now this angle right in here is 53 degrees. And we know that because of the angle in here is 50. And then if we drop a vertical line down here, this is 90, and then this would be 90 minus 53, which is this angle right in here. So the angle that is made with respect to my y-axis is going to be 53 degrees, and that force. So now we're ready to apply the sum of the forces. Remember that this system is accelerating to the right. So we're going to write sum of the forces in the x equals m1a. We have the tension to the right. We have the force of friction to the right. But we have the x component of that gravity, Fg1x. It's acting to the left here. And then this all adds up to ma as the net force. Let's expand these two terms here. Tension we'll leave as it is. But now we're going to rewrite the force of friction as the coefficient of friction. It's moving, so it's mu k times the normal on that block M1 minus m times g. Instead of using m1, I'm just going to use m because that is the same mass. And then times the sine of the angle given, which is 53 degrees. And this is all equal to m times a. And again, I'm just replacing m1 just with m now. Okay, now I need to take this a little bit further and find out the normal force. So let's look along the y-axis here. Maybe we'll just do that over here. The sum of the forces in the y equals 0. Maybe I'll just rearrange this page a little bit more so I have some more space. Hold on. Okay, so here I've just rearranged it. So now along the y-axis here, the normal force Fn1 will be balanced out by the y component of that force of gravity, Fg1y. So Fn1 is equal to m times g times the y component, and this would be mg times the cosine of the angle, which is 53 degrees. So now we're going to sub this expression into here. So now we'll have the tension plus mu k times m g cosine 53 degrees minus mg sine 53 degrees is equal to m times a. And we're looking for the acceleration in the end. So if you look closely at this expression, we know m's, we know g's, we know the angles. We don't know the tension, nor do we know the acceleration. So we'll need to eliminate the tension. We have one equation with two unknowns. So where's the second equation going to come from? Aha, block M2. So let's go on to that now and redraw that one. Okay, so once again I've taken this free body diagram and I just tilted it just to look a little easier for you. So this is the normal force Fn sub 2 right here. Here's the force of friction F2 going in the opposite direction to the right, but it's actually accelerating to the opposite direction that it was moving, which was the left. We have the force of gravity Fg2, and then we have the tension Ft. That is common with the tension over here for block M1. Now this angle here of 30 degrees, again, if you drop a vertical line here, this is 90, and then this angle here is going to be 60 degrees, so this must make this 30 degrees. So right in here, between this force and the y-axis is an angle of 30 degrees. Okay, so once again, we'll apply Newton's second law along the x-axis, where this is accelerating to the right here. So sum of the forces in the x equals m2 times a, and the forces that are causing it to accelerate in that direction, we have force of friction Ff2, we have the the x component of Fg2 Fg2x, and then we have the tension going in the opposite direction, so that's negative here, and this all adds up to mass 2 times a. So let's expand the force of friction and write mu k times the normal force Fn2, and then we have the x component of that weight, that's going to be m times g times the sine of 30 degrees. Then we have minus the tension equals m times a. I've replaced m2 with now just m's because that's what it is. Okay, so we'll need to get rid of the normal force, and that's going to come from the sum of the forces in the y is equal to 0, and Fn2 minus the y component of Fg2, weight of that. So that's going to be the normal force, number 2, will be equal to mg times the cosine of 30 degrees. And now let's sub that expression into here, and so we'll have mu k times mg cosine 30 plus mg times sine 30 minus the tension equals ma. And so once again, you have another expression where you have a tension and a tension and an acceleration and an acceleration, and we need to solve these two equations. So let's call this equation number 1, and we'll call this equation number 2, and we need to work with the two equations. You could add them together and then the tensions will disappear. Or you can rewrite this expression for tension by itself and plug it into that. So now it's just mathematics. Alright, so we're now going to take equation 1 and add it to equation number 2. And so what we'll get is the tensions will disappear because this one's positive and this one's negative, and you'll get mu k g cosine 53 minus mg sine 53 plus all of this, mu k times mg cosine 30 plus mg sine 30. And then when you add the two sides on the right side, that is going to give you 2 times ma. And I just realized I'm missing a little m in here. Let's add that in there. Now you'll see that there is an m in every term, and they're all the same mass, so they all can cancel out. And we have a g in every term, and so we'll get the following. G, the acceleration, is equal to g divided by 2, because I'm divided by 2. And then we'll have mu times the cosine of 53 minus sine 53 plus mu times the cosine of 30 plus sine 30. And so all we need to do at this point is substitute in here. We have 9.8 divided by 2, and then mu is 0.3 times cosine 53 minus sine 53 plus 0.3 cosine 30 plus sine 30. There's a lot in this expression, so it's easy to make mistakes. And you should get an acceleration of 0.694 meters per second squared. So now the last part is to substitute that into your kinematics equation. Let's use v squared equals v0 squared plus 2a delta x. Our final speed is 0, so 0 equals our initial speed of 0.9 meters per second plus 2 times the acceleration, 0.694 meters per second squared times delta x. And that will get you an answer of 0.583 meters. So quite a long problem. I think it would be a bit too tough for an exam, but if you really know how to do this on your own, this is a very good problem. And you really know your stuff. Okay, and that's it for this example.